Okay, I just uploaded a video explaining Newton's first law and Newton's second law, and I said I was going to make a video to explain Newton's third law in a separate video. So, first of all, thanks for watching any videos that you have watched. Don't forget to like, share and subscribe. We do appreciate all the support we can get. This is a new channel. I started it in December last year as an experiment to see if it helped my students, and then I saw how successful it was in helping students in other countries, perhaps where they don't have access to a full-time physics teacher. And I'm getting a lot of positive feedback from students around the world, mainly in Asia, where I'm situated. So I'm going to go through today's video. It does take a bit of time making these videos, so please make sure, even if you got something out of it, to give us a like, share it with your friends, and when you subscribe, you'll be notified when the next video is uploaded. The main focus up to now has been A-level videos, and now I'm making some quick revision videos using my PowerPoint slides. So today's video is on Newton's third law and momentum conservation. Okay, so while you're watching these videos, I would recommend that you make notes, so you can stop the video whenever you want to and make sure you've got a good set of notes. Okay, so here, Newton's third law of motion. So we did say Newton's first law and Newton's second law of motion are analyzing the motion of a single object. Okay, they're looking at the forces on that object, and if they're balanced, it's Newton's first law. The object will continue to move at its rate of velocity, or if it's stationary, the velocity is zero, so it won't change its velocity. And if it's Newton's second law, we're talking about when the forces on the object are unbalanced, and in such a situation, the object will accelerate in the direction of the unbalanced force, okay? Also known as the resultant force. In Newton's third law, we're actually looking at two objects simultaneously interacting with each other, okay? So we're talking about pairs of forces. So we talked about, so a common way of saying it is when body A exerts force on body B, then body B exerts an equal and opposite force on body A. So this can be thought of, for example, that with orbiting objects, for example, the moon is exerting a force on Earth. At the same time, the Earth is exerting the force on the moon. The motion of the two bodies is not what we're talking about. We're talking about that if they are having a force on each other, it works two ways. And this actually Newton's law of gravitation, which comes in A-level, and I normally teach it at the end of GCSE when we do astrophysics. These two forces are equal and opposite in directions, but they're acting on two different objects, okay? The reason the moon, for example, moves around the Earth is because it's the less massive of the two objects. So the effect on the smaller mass will be greater in terms of motion than the effect on the larger mass. The same applies with the Earth and the Sun, okay? The reason the Earth goes around the Sun, or it appears that that's what's happening, doesn't mean that the Earth doesn't have an equal pulling power on the Sun. It's just the effect is different on each one, and that's what we're going to look at in today's video. Okay, so Newton's third law is the law of action and reaction. Yeah, two objects which simultaneously are affecting each other. Okay, so here we got two identical objects, Newton's on skateboards, and the reason we're using skateboards is because we need to get rid of friction for us to do our thought experiments. Okay, so what's going to happen? So Newton on the left says, my third law says, if I push to the right, where there's an equal and opposite Newton, yeah, a mirror image of the Newton, if I push to the right, I will move backwards as well. Well, if you do ice skating, or you go on an ice rink, or you got good roller skates, and two of you are pushing hands against each other, you both move backwards for you, yeah? So let's watch what happens when the forces are applied. So the forces are equal and opposite, yeah. Newton A and Newton B, yeah, act as body A and body B. So when they push against each other, yeah, they both move in opposite directions because they're both exerting equal but opposite forces on each other. The direction is opposite, but the sizes are equal. Okay. So what else do we need to consider when we're looking at this thought experiment? So I've put each object will gain the same amount of momentum but in opposite directions or in opposing directions. So when that happens, the Newton on the right will be moving to the right with momentum to the right, and the Newton on the left will be moving to the left, and his momentum will be to the left. Remember, in the last video, if you watched it, I said momentum is also a vector quantity, so you need to take the direction into account. Okay, so as they're pushing each other, yeah, the effect, Newton on the right will move to the right with a specific amount of momentum, his mass times his velocity, and likewise with the momentum for Newton A on the left. Okay, so if their masses are equal, their velocities will be equal, but in opposite directions. Okay, so what is momentum? So first of all, we need to understand what momentum is. Okay, so any moving object has momentum. Yeah, so a momentum, an object that has both mass and momentum, mass and velocity is said to have momentum. And we often use a symbol P for momentum, yeah, in equations, especially at A level. It can also be used in GCSE. Okay, so P is equal to M times V. Okay, normally we use small m, so I think that should be written as a small m when you're doing it. And P also is small, and so should velocity be. Okay, so you need to know the units. The units for mass, obviously, a kilogram. The SI units for velocity or meters per second, and that makes the unit for momentum as kilograms meters per second. Okay, now the pages referenced here are for my students because we use the Edexcel IGCSE textbook, so if they want to learn more about it, they can go and research those pages, but you would have to find whichever textbook you're using for your own benefit of how momentum and Newton's second law can also be linked. Okay, so I'll leave that for you to research. And what happens to a space vehicle's momentum when it fires its rocket engines? Okay, which law applies when a rocket fires its engines? Okay, you may have thought of this before, you may have discussed it before. Okay, it says you need to learn this equation. They're reviewing currently for GCSEs which equations will be given, which equations won't be given. Normally in the Edexcel IGCSE exam, this is one where you have to learn it. Okay, back to Newton's third law, yeah? So going back to the same Newton with the skateboard situation, the next question I said, what if one of the objects had twice the mass of the other object? So obviously the two Newtons are identical, so it's not going to happen in my slide. But if one mass was twice as much as the other mass, yeah, the momentum in each direction must still be equal and opposite. But the one with twice the mass would be more difficult to move, therefore its velocity would be halved, and the mass, which is singular, would have twice the velocity of the heavier object. So small mass, large velocity, large mass, small velocity. Okay? Now I haven't shown it going at different speeds in this slide because I don't know how to do it on PowerPoint. Okay, this is basically a PowerPoint to animate and go through the concepts. So these videos I make are to explain concepts to you. Okay, they're not accurate representations of what really happens in physics in the real situation. So here we got the same question, but this time we got into space, and that's a satellite in space. And if an astronaut comes along, hopefully he'll have a helmet on. I think that's meant to be his helmet, so he presumably has brought his own air with him. And the same thing applies. What happens if the astronaut by accident pushes the satellite? Okay, what will happen if I push this satellite away from me? Well, the object is already moving in space, but if you imagine them relative to each other, they're stationary. They're both moving with the same velocity because they're stuck together, as it looks on the screen right now. So if the astronaut, as we'll call him, if he pushes a satellite away from him, then according to Newton's third law of motion, he should move backwards. Okay? What's the problem with this image is that they both move off with the same velocity. In reality, the satellite will be way more massive than the man. Therefore, the satellite's motion or velocity will be smaller, whereas the less massive man will move backwards with a greater velocity. Okay? And that's similar to how rocket engines work. So let's see what he has to say about the next concept. How will the effect differ for each object, and explain why? Well, that's what I just explained to you. Because the masses are different, the velocities will be different. But the momentum in each direction, if it's zero momentum between them right now, if at the end one will get positive momentum and the other will get negative momentum, and if you add them together, mathematically they should add up to zero. So if their total momentum as it appears on the screen right now is zero, then the total momentum after they push each other apart, or there's interaction between them, then afterwards the total momentum to the right will be counted as positive, and to the left we can count it as negative. The total amount to the right, momentum-wise, will be equal to the momentum to the left. Okay? So, I hope that makes sense to you. This is basically what we're talking about, and this is called the conservation of momentum. In any such interaction where forces are involved on two different objects, momentum must be conserved, provided that there are no other external forces involved. So obviously if we're in outer space and the astronaut is just pushing the satellite and there's nothing else around and no other external forces are acting, the smaller mass, however, will gain a greater velocity and the larger mass will gain a smaller velocity. But the momentum must be the same in the two directions, or the momentum change must be the same to the right and to the left. Okay? Mathematically, graphs to the right are positive and graphs to the left are negative. So that's a common way of putting positive and negative velocities as well. Okay, so this is exactly the same. We're just making you have the understanding that the momentum to the right and the momentum to the left must be the same, but they will not move with the same velocity if they have different masses. Okay, so that happens with a gun. When you fire a gun, the bullet goes out in one direction with a high velocity, but the gun moves backwards because the gun is attached to the person shooting it. The mass of the person and the gun is much greater than the bullet, so the bullet gets a lot of velocity and it has a small mass, whereas a recoil momentum is the gun and the person holding the gun will move backwards with a smaller velocity. Okay, so remember that momentum is mass times velocity, and if you want to practice these questions, you can. Archie, 50 kilograms running at 10 meters per second. Multiply the two together, you get 500 kilograms per second, kilogram meters per second. And then a car traveling at 30 meters per second, 1,000 kilograms times 30 meters per second will be 30,000 kilogram meters per second. And a small pen, 20 grams, so you need to change the grams into kilograms like they've done for you. Don't be tricked by that in the exam. You need to use kilograms, meters, and seconds. Okay, so the answer will be 0.1. Okay, and then Mr. Richards has a mass of 90 kilograms. If he bungee jumps and falls at 40 meters per second, while he's falling at that speed, you multiply his mass by the speed and you'll get his momentum as he's falling at that speed. Now, conservation of momentum in any collision or explosion, momentum is conserved, okay? Because forces are involved on the objects, provided there are no other external forces acting. So we're talking about just a simple exchange of forces between two objects. So we don't want to complicate things by adding in external forces as well. So an example of a collision would be a car collides, well, one car collides with the back into the back of another car, and they stick together and they move off together. They kind of just become locked together when they do. What speed do they move off at afterwards? This is what we're looking at. So here's the car in the front. It's moving forward at a 20 meter per second speed. Yeah. It's got a mass of 800 kilograms. And then another car, a sports car, is coming behind it and it's going 50 meters per second and not taking care. It's also got a bigger mass. So the car at the back has more momentum. The car in the front has less momentum. And the driver is obviously not thinking. He doesn't put on his brakes fast enough, and they come and they collide afterwards. And what will the speed be afterwards? Well, we know the mass afterwards, if they're going to move off together, yeah, they stick together. Their bumpers, assume their bumpers get locked. So we know the momentum before must be the mass of the grey car plus the mass of the green car, because they're both moving to the right. And then you know the mass of them together must be 1,800 kilograms. So the only thing to work out is what is the velocity afterwards. Okay? So how do you do it? Well, initially you have to state that the momentum before must be equal to the momentum after the collision. Yeah? We're talking about just before and just after, before frictional forces have had a chance to take an effect on slowing down the cars after the collision. So we're talking about instantaneously what will the momentum be after they move off together. Okay, so at the beginning we had 1,000 kilograms times 50 meters per second here, plus 800 kilograms for the green car moving at 20 meters per second. So that's the total momentum before, M1V1, yeah, vehicle 1 or vehicle A, MAVA, and MB, vehicle B, times VB, MB times VB. That's a total momentum before. You can add them up together. Afterwards, the mass of the two cars locked together will be 1,800 kilograms. So the only unknown is the final velocity of the two cars locked together. So you should be able to work out algebraically what V would be equal to. Yeah. If you can't, here it is. It will be 36.7. So basically, you've got to multiply these two numbers together, add them to these. So you could have brackets around these, and then divide by 1,800 to get the V, and hopefully you'll be able to work it out using your algebraic skills. Okay? The second example would be what happens if the cars collide head-on. Okay? If they're moving in opposite directions. Yeah? So the grey car is moving to the right again. This time the green car is coming towards it with the same velocity that we had before. Now this time we have to count one velocity as positive and the other velocity as negative. Work out, because momentum is a vector quantity, so the momentum of the second car, the green car, is negative. Okay? So the total momentum before will be not adding 1,000 times 50 with the 800 times 20, but taking away the 800 times 20. So you now know the total momentum will be 3,400 kilograms meters per second in the direction to the right, because that's where the momentum was larger. Okay? And afterwards, the speed after the collision, if they move off together, it will be 3,400 kilograms meters per second, which was a total momentum before, divided by the mass of the two cars, and we have to assume they're going to move off locked together, otherwise it's too complicated for GCSE. Divided by the mass, you get the velocity after the collision. Hope that makes sense. If it doesn't, you need to go and read the chapter in your book on conservation of momentum. Okay? So here's some more questions that you can look at, and if you want to stop the video at this stage and see if you can use the same mathematics that I've shown with the cars, and you'll be able to work out momentum conservation questions. And freeze the video now if you don't want to see the answers, so you can do that, because I'm going to put the numerical answers up next. Okay, first answer is up, second answer is up, third answer is up, and the fourth answer is up. So if you want to go back and do each one you can. And then there are some more questions here. Likewise, if you want to stop the video, try to do them, and then you can restart the video when you have tried both questions. Okay, the answers will come on the screen. Okay, so there's one final situation where is a more it's an explosion, if you like, and it's linked to nuclear physics. So consider a heavy element, nucleus of an element, americium or americium. I prefer to call it americium, but I think it's pronounced americium, named after America. So that's why I like to call it americium. So this is a man-made element, so it's actually unstable. And what happens is that it decays, and it decays by way of emitting 2 protons and 2 neutrons from its nucleus. And when that happens, it basically wobbles around for a bit and shoots out, a bit like a gun, a bit of itself. And the alpha particle has 4 units of mass, whereas the americium had 241 units of mass, protons and neutrons being roughly equivalent in mass. So you know the mass going backwards and you know the mass going forwards, and therefore you should be able to tell that at the beginning, when we were in just all the protons and neutrons were in together in the form of americium, then the total momentum was 0. It wasn't moving. It only started moving when it shoots out a bullet like an alpha particle. Yeah, so the alpha particle gains positive momentum to the right, and the larger nucleus moves to the left, and in the process it loses 2 protons and 2 neutrons, which makes it a different nucleus. It actually changed to something called neptunium. Okay, so can you analyze this in terms of conservation of momentum? And this is a higher level question, probably better for students preparing for A-level. So if the new neptunium atom, the nucleus moves backwards at a speed of 5 times 10 to the 5 meters per second, what was the speed of the alpha particle? That's the question. So remember that each of the 2 protons, 2 neutrons, count them as 4 mass units for the alpha particle, and count the neptunium moving backwards as 237 mass particles. Okay, so call it 237m and 4m, okay, to the left and the right. And you should come up with this answer if you can work it out. Okay, so I'll let you struggle through that. So that's like an extension question for GCSE students, and it's the kind of question you would be expected to answer easily if you do advanced level physics. Okay, now I know you haven't done nuclear physics yet, but you have enough knowledge from conservation of momentum to be able to analyze what's going on using the conservation of momentum equation that we went through in the previous slides. Okay, so remember, going back to this first slide where we did a conservation of momentum question, the equation was here that the total momentum before must be equal to the total momentum after. So you've got to apply this principle to the nucleus, which shoots out a bit of itself to the right, and it recoils backwards, just like a bullet and a gun being held by a person. Okay, so this is how we did this one. So you've got to apply what you've just learned to solve the problem, and do as many of these questions as you want to. This is what I want you to solve. Okay, you need the masses of each particle, and then you can work out from the ratio of the masses, you should be able to work out the ratio of the velocities. And if you know one of the velocities, then that makes it possible to work out the velocity of the other particle. So I hope you found that interesting. Once again, thanks for watching. Don't forget to like the video if you found it helpful. That really helps us go up in the YouTube algorithms. My aim is to get 1,000 subscribers as soon as possible, and then YouTube will actually monetize my channel for me. Share it with any friends you think will find this video helpful to them, and subscribe to ensure you get notified when future videos are uploaded. Okay, hopefully see you in the next video. That's it for now. Bye.